Hello and Hare Krishna. Welcome back to the Atma Paradigm. This is session 3 of part 4 of our series, which is the universe and beyond. And we're continuing to explore a universe of information. And today that leads us to the question of what is there at time t equals 0? The beginning of the universe as proposed by the standard model of cosmology. Now we begin with a little recap. Last week we discussed that out of our 4 big questions, consciousness, matter, life and the universe, there are standard models within physics for only 2 of them. A standard model for particle physics and a standard model for the formation of the universe. I think it's worth reflecting on 2 points. Currently, the standard model for matter, particles based on quantum physics, has not really been adequately resolved with relativity, which is the foundation for the standard model of cosmology. So it's understood that something's going to have to give in 1 or 2 of these models or have to be added to them in due course. Secondly, and this is my view, it seems incongruous to suggest that we can have a standard model for only 1 or 2 aspects of reality, but not the others. If we can't resolve consciousness and life with the models for matter and cosmology, it seems hard to claim that the basic explanations for matter and cosmology are settled. So I think we really need a standard model that addresses all of these topics together. Even so, last week we gave an outline of the history of the development of the ideas that have been incorporated into the standard model of cosmology. And this provided an inkling of the extent of information that we need to account for in the conditions of the early universe and in what we see today. We explored the issue of free parameters. Now, cosmological free parameters, they're in cosmology and also in physics, are specific numbers of values and ratios of properties that cannot be generated from theory. They are the actual values observed to be within the properties of matter. Hence, they're free parameters. They're sort of primeval values. They are what they are. Why? Because that's the way they are. And there seems to be no way of explaining why they should have that particular value that they have. It's just the way it is. But the interesting aspect of all these parameters is that although theory cannot predict why matter has these values, and therefore we'd expect these actual values to be arbitrary, but what we find is that these arbitrary values, in inverted commas, are critically precise to being exactly what they need to be in order for the universe to exist. An important one that we discussed, for instance, in detail last week was the value of omega. This is the ratio of the actual density of energy and mass in the universe to the critical density of the universe. Critical density is the only value for the density of the universe, i.e. the amount of matter in a particular volume, that produces a universe that forms stars and planets and stays around long enough for us to live in it. So actual density divided by the critical density must equal 1, exactly. That's the kind of value of omega. It must equal 1. And it has to equal 1 to 60 decimal places, which it does. Now this poses just one of the issues for cosmologists to explain. Why should something in the universe have has a physical numerical value that precisely matches the only value that will give rise to an inhabitable universe, a place for life and consciousness, at least on this planet, if not anywhere else? So this raises the issue that our universe appears to be fine-tuned for its formation and continued existence, and even more so fine-tuned for us to be alive within it. So we surely live in a universe of information. There is precise information in the starting conditions of the universe, or at least there is information in these values which produces results. There is new additional information in each of the components of matter and each of the fundamental forces, and there is new extra information that has not been shown to be the product of the values and information of things that came before it. It's free information or free parameters. There's also information in the laws coordinating space and time, and information locked away in the structure of galaxies, stars and planets. Now, we approached the phenomenon of a universe full of information last week by telling this part of the story of the development of the ideas behind the Standard Model. And we did that so that we could understand the key aspects of the model and the rationale behind them. Now, we're about to go on the hunt for the sources of all this information. But before we do that, we should remind ourselves that the key principle to keep in mind when we consider issues of information and complexity of the world is this little thing we call entropy. Entropy is a feature of how nature behaves, and it relates to information content. So what is entropy? Well, it's understood in physics as a measure of the state of disorder of a system. So the higher the entropy, the more disorder. For instance, the sand on a beach is high entropy. You can arrange the sand particles in an unlimited number of ways and you still got a kind of the same basic beach shape, same simple information state. And we can represent that as we've shown in our little diagram, that high entropy state like these little squares or cubes in a loose, non-specific arrangement. Whereas a sand castle requires a specific arrangement of the sand particles in order to manifest its particular form. So this is a state of lowish entropy, and it contains a fair amount of information. So we can represent it in our little diagram with like a stack of these little cubes. Now, it's taken someone time, effort, and the input of intention, thought, and information to produce the low entropy state of the sand castle. But if we just leave things to nature, entropy inevitably moves in one direction. Entropy decreases, and eventually it evens out with its environment. That is nature's way. And anything other than this requires us to postulate a source of information. So if we have a situation where a sandcastle is produced out of sand, we have to ask the question, what was the source of that information? And it needs to be information that is sufficient, useful, and specifying. So what is the source of the sufficient, useful, specifying information that has produced this structure and taken a situation of high entropy to a position of low entropy? Now, one more thing also before we get started is we're going to have to acknowledge that acquiring observations about the cosmos and piecing together all these theories on how things might have happened is extraordinarily difficult. So we need to recognize the huge challenge that our cosmologists and astrophysicists undertake, because the cosmos contains mind-boggling scales of distances and so many different features, many of which are mysterious and some of them are just downright weird. So the range of concepts and the interactions between all these different concepts that cosmologists are dealing with, it's a marvel. And the picture they are trying to reveal is the result of slow, methodical process. So we have to appreciate the challenge that they've undertaken. And I can't here give a full analysis of every idea and theory that seeks to explain all the different phenomena that exist. However, the claim of the Standard Model is to be a framework that can address in principle and in due course all existing and future questions and mysteries. So I think it is reasonable, therefore, at this point of its development, it should be able to handle certain broad philosophical matters. And that's going to be our approach. We're not getting into the details of every little thing, but we want to take this particular approach. So we want to identify the key philosophical ideas and principles behind the origins and causality upon which the Standard Model is constructed. We want to be able to explain the implications of these ideas and principles in terms of their ability to account for information and complexity, along with other features, which we'll talk about at another time, time, matter, and reality. And we also will consider the limitations that naturally are there and beset the Standard Model, not because of the limitations of technology and where we are with our discoveries, but because of the boundaries of epistemology. And by that I mean when science reaches those boundaries beyond which it has to conjecture on matters which are beyond direct observation. So, without rejecting the valid insights of the Standard Model, we'll today and next week be offering suggestions of new and additional factors that might help to remedy some of the incongruities of the model. So let's consider that we start with what we know we have now. What's out there in the universe? And cosmology thinks of this in two ways. It thinks of it in terms of the structures that make up the universe and in terms of the composition. What are the components of matter that make up the universe? Now, you might think I should take composition first, but because the factors arising from the way cosmological structures behave, those factors have influenced how cosmologists think of what is the actual material makeup of the universe. So we have to start with the structures. And there are stars in various stages of their life, and associated with most stars, as far as we know, are planets. And these form different planetary systems around their stars. And the stars in their systems exist in huge numbers within galaxies, probably spinning around a black hole that may be at the center of their galaxy. And galaxies form into clusters, bunching up in groups of various sizes. And these are the structures with forms. Now, there's a lot of other cosmological features out there which are in the kind of amorphous state. But generally, stars, planets, galaxies, and clusters, these are the stuff that's visible and makes up the actual structural stuff of the cosmos. Now, what we're now looking at is all of those planets and galaxies and stars and everything makes up just a tiny part of what is categorized in terms of the composition of the universe. The proportions of all the actual matter stuff is described in pie charts like this one. Numbers are going to vary a bit from chart to chart, but it doesn't really affect the general ratios between them. So there are three main components. There's the visible stuff, the actual matter we can observe directly. That's the stars and planets and everything else, you know. And then there's dark matter and dark energy. Now, the visible stuff is reckoned to account for only 4% of the whole mass of the universe. And out of that 4%, the vast majority, nearly 4% itself, is free hydrogen and helium just floating about the cosmos. The rest, a tiny fraction of 1% of the whole, can be broken down like this. Stars make up about half of this less than 1% that's left. And this is sometimes called the luminous matter because it's the bit that's undergoing all these nuclear reactions and throwing off incredible heat and light. And the next major aspect are neutrinos, kind of ghostly particles, which are almost zero mass and no spin and very rarely react with the rest of real matter. The remainder, and it's just 0.03 of 1%, is all the other stuff of the universe other than hydrogen and helium. But if we can see only these visible bits of the universe, why does the Standard Model propose that there's another 96% of all the mass of the universe that we haven't yet detected directly? And the first one we'll deal with is dark matter. There's 23% of the universe is suggested to be dark matter. And the reason for this goes back to physicist Fritz Zwicky in the 1930s. He noticed that the Andromeda galaxy was spinning so quickly that it really should be falling apart at the edges. The centripetal force for the stars and planets in their outer areas would outdo the gravitational force from the galaxy pulling them in. And so it's like if you tie a heavy weight to a string and whirl it around. Now, the strength of the string might not be enough to hold the weight in its circle, and the string snaps, the weight will fly off. And that's what Zwicky thought maybe is happening to the the galaxies for at least for the stars and aspects on the outside. And it was Vera Rubin who then measured the rotation curve of Andromeda herself, and she noticed that the speeds of the stars at the outside of the galaxy, say at point A on our little image, the speed there was the same as B, when really they should be needed to be much slower. So she suggested in 1970 that a vast part of the universe was missing. There must be far more mass associated with a galaxy than we can see in the stars and planets. And this missing stuff must have mass and be able to produce a gravitational effect. But somehow it didn't interact with electromagnetic radiation, therefore it wasn't detectable visually. So that's why it's called dark matter. Now, in the 50 years since Vera proposed dark matter, there have been all sorts of conjectures what type of matter this is and what type of particle dark matter might be. And they've given some great names like MACHOs, which is a massive compact halo object, or a WIMP, which is a weakly interacting massive particle. Oh, and there's axions and gravitons and other things. And with each particle theory, there's been some strenuous efforts to detect them, so far without success. Some cosmologists think that the search is futile because maybe we got their interpretations of the observations not quite right, and maybe we don't need to theorize dark matter. But and others kind of suggest, well, maybe we just need to change how we look at gravity. And there's a theory called MOND, Modified Newtonian Dynamics, which tries to do away with any need for dark matter whatsoever. But to date, dark matter is a key component of the Standard Model, and whatever it actually is, it's said to play an important role in the development of the galaxy structures, which we'll talk about in a little bit. Meanwhile, while the worry is, where is all this dark matter, another type of stuff kind of emerged from the woodwork, and this is dark energy. Different, don't mix them up. Now, with dark energy, there's actually 3 times as much of this invisible stuff as there is of the dark matter. And it's thought to make up 73% of all energy and mass in the universe. And dark energy has been proposed because of another issue in the universe. Cosmologists have been measuring light coming to us from exploding stars called supernovae. And the Standard Model predicts that the expansion rate of the universe should be slowing down as time goes on, thanks to the effect of gravity. But that's not what the measurements of the supernovae indicate. Space is expanding and the rate of expansion is accelerating. So this indicates that there must be some other force acting on the matter of the universe, but in the opposite direction of gravity. If gravity is pulling things together, then dark energy seems to be pushing them apart. So our diagram here shows the 2 opposing forces. Gravity trying to slow down the expansion so that the 2 arms of the arrow, the blue arrows, should be converging. But dark energy has a greater effect, it seems, and is pushing the arms apart. So space is expanding ever more quickly. So what is this hypothetical stuff called dark energy? Well, we don't really know. Currently, there are still no viable contenders, and therefore no specific experiments devised for its observation. So the debate goes on, and again, the same sort of questions come up. Have we made the wrong assumptions about the homogeneity of the universe? Is there some kind of turbulence from the early universe that's kind of causing this? Have we miscalculated what our observations from the supernovae? So I think these examples of dark matter and dark energy illustrate a comment I made last week, that we are eager to postulate unknown exotic factors to balance calculations of missing mass and energy, but don't seem as ready to postulate factors that might be needed to balance missing information. So much more attentive to mass and energy than we are to information. Yet missing information is at the core of the conundrum for what has been called the Goldilocks universe. Now, I've mentioned this term before, but in case any of you are not familiar with the reference, this goes back to a fairy tale about a little girl with golden hair. That's why she was called Goldilocks. And she liked everything to be just so. Now, in short, the story goes like this. One day, she illegally broke into a house belonging to 3 bears. Mama bear, daddy bear, and baby bear. And the bears had laid out some porridge in bowls on the table, just as each of the bear family liked it. Goldilocks tasted the first bowl, but it was too hot. She didn't like that. And the next one was too cold. She didn't like that. But the third one she thought was just right. And she goes about the house discovering something that's like just too much this, too little that, but something else is just right. So in the same way, the universe has this quality. Aspects of it are not too much of this or not too little of that, but just right. For instance, the measurement of extragalactic background light. And basically this works out the total sum of all starlight in the cosmos known to astronomers. And it gives a flavour of the quantity of stars that are out there in the galaxies. And when we look out, we find that there are not too many stars, nor too few, but just the right amount of stars for the universe to form and continue to exist as it does for us. So this is the idea of the Goldilocks universe. Everything in it is just right for it to be here. All the free parameters, the constants and the conditions are just right. Now we've already mentioned the constant omega, which was included in a list of 6 numbers that Martin Rees, the UK Astronomer Royal, regarded as crucial for a kind of Goldilocks type universe. And here are the others that Professor Rees counts as vital. The first one is epsilon, which is the strength of the weak nuclear force. This determines how firmly the atomic nuclei binds together. Now, get that wrong and you're not able, stars can't turn hydrogen into other elements. And if this force is a different strength, then none of the other elements, the atomic elements, could ever be formed. You just have hydrogen. Next one, N equals 10 to the 36. This is the ratio of the electrical forces holding atoms together divided by the force of gravity between them. So it's a ratio. And if this number varied even just a little bit, there would have been a miniature short-lived universe, and it wouldn't have existed long enough to form the universe as we know and for us to be alive within it. Q equals 1 over 100,000. And this represents the amplitude of complex irregularities that become galaxy seeds. Now, that's a difficult concept, but we're going to talk about galaxy seeds a little bit later. But the point that Rees is making is that a smaller ratio would mean the universe is just inert and structureless. And if it was larger, it would make it turbulent and just full of black holes. Again, wouldn't be a useful universe. And lambda is the force that is accelerating the expansion of the universe. Fortunately, that is just right so the galaxies and stars can form. And one more, which is a little bit of a surprise to hear it mentioned in this context, is D. There are 3 dimensions to space. Now, I think for most of us that sounds pretty obvious, but the standard model offers no reason why the universe should present just 3 dimensions of space. As we experience it, space is said to expand from 0 dimensions, i.e. it was a point, so it could have stopped at 1 dimension or 2, and producing 3 that forms the world of our perception is just right for us. Now, in a previous talk, I think it was in part 3, I used a chart showing energy rate density. This gives a measure of the amount of information passing through physical systems. Or you can think of it as the amount of information contained within a system that specifies it and specifies what it does. So that's true whether that system is a star, a planet, or a technological society. So here is the chart that has been worked out, and there's been numbers of versions of this by different groups. And here it is plotted to show how the amount of information during the period from the start of the universe, 13.75 billion years ago, until the formation of the Milky Way galaxy, then the sun, and then the planets like Earth in our solar system. Now, that's all the yellow area. So the message of the chart is that we live in a universe of much greater information content now than in the early stages of the cosmos. So our situation is that the now of the universe is a now of high information content. And that level of information has to be accounted for. And we have understood, when we looked at things last week, that we accept that the universe has a past, and in fact a past that has a starting point. So we can ask, what was the information content at that point? Was there useful information inherent in the starting conditions of the universe? Sufficient, useful and specifying information inherent in those starting conditions? If so, had got the quality and the quantity of that inherent information? Was it in itself sufficient to explain the content and complexity of the forms and structures we observe now, as well as explaining the precision of the various free parameters? And if that's not the case, then were there any additional factors available during the process of the development of the universe that would account for the build-up of information, the additional novel information that seems to have come into the system over time? So those are our questions. What's the information state at the beginning? And was there ways on which information could come into the system during its process? So let's travel back to the starting point and ask, well, what was there at the start? What happened next? So what there at time t equals 0, the beginning of the universe? Now, there's much debate how to answer this question. And part of the reason for what people are arguing over about what is there at the beginning of the universe is a result of how they have analysed what seems to have happened subsequently to the start. Now, and that's why we're not going to be able to go right back to the start today. We're just going to make the assumption that the standard model uses. Now, it's important to remember a point we made last week, that cosmologists have no way to see back directly any earlier than the point of recombination when the cosmic microwave background was released 380,000 years ago. Now, that was the point when the atoms formed as atoms and photons were then free to move in space, producing the effect of the cosmic microwave background. So because of that, we are not able to observe anything directly before then. So the standard model is a conjectured description of what might have happened before this point in order to fit what we know is later produced. But it uses the assumed Big Bang starting point and the simplicity of the idea of a singularity. So the standard idea is that the universe starts with a singularity, which is a point of infinite density. So all the energy and mass of the universe is contained in 0 volume of a point. Now, this is a state, a concept that is beyond mathematics, and we'll see soon that our major questions and doubts if a singularity could actually be the start, because the mathematics and the physics start to break down before you get to that pure point of the singularity of a point. So, but in our explanation of what happens next, according to the standard model, we're going to join the action just a fraction of a second after that starting point. And so at this point, the universe was inconceivably minuscule still, and it was just some plasma stuff. And then we talked about this last week at time 10 to the minus 43 seconds. There was a period of inflation when the universe expands by 40 to 50 orders of magnitude. Now we say period of inflation, but it all seems to have happened in a blink, way before the clock reached 10 to the minus 33 of a second. So within 0.00000001 of a second, the universe grew by 10 trillion times. It's inconceivable. And then, as we mentioned last week, inflation stops. As suddenly as it started, it stops and slows to the perfect slow pace of expansion that is absolutely fine-tuned and precise to produce a structured universe. So what happened during the period of inflation? It's very important. Space itself is expanding. The idea of the Big Bang is an explosion of matter. It's not an explosion of matter, it's an explosion of space. And this space is empty, or at least it is statistically empty. It doesn't mean that there's nothing exactly. It just means that on average, the manifest physical stuff equals zero. The physical energy that is manifest equals zero. So it's like a quantum vacuum, but things are happening. And what's happening is that constantly virtual particle pairs pop out of the vacuum and into a kind of virtual, it creates a kind of foam of stuff. It's a virtual kind of form of not quite real reality, because each pair is composed of one particle of ordinary matter type stuff and one particle of antimatter. So we've got the positive and the negative. In this sense, it's not electrical. This is ordinary matter and antimatter. And because they effectively remain a pair, the positive and negative energy between them cancel each other out mathematically and energy-wise. So the nothingness of energy and mass is conserved, even though there is this virtual pair bouncing around. And almost as soon as they appear, they will collide. And when they collide, matter and antimatter, just annihilate each other, and they will disappear out of existence again. So they've sort of existed, but not in any real meaningful sense in physics terms. Now, the combined energy of all the pairs is called the vacuum energy. So this vacuum has some energy. Note, this is the first thing that is supposed to happen after Big Bang. And this is the beginning of matter and information that such matter contains. So it is important. Now, these vacuum fluctuations are quantum-based, so they're considered random. There is thought to be no source of information within them determining when or where they occur. They are just random kind of fluctuations of some underlying quantum state. So according to the standard model, this is a very, very, very low information state. Very, very high chaotic entropy. Now, if things had persisted like this, with this kind of vacuum just popping these pairs which come into existence and then annihilate each other, disappear again, then nothing more would have happened. But something did happen during this time, and that was inflation. So during inflation, space is being stretched, and the two particles that were a pair are now being separated, as in our little diagram here. Instead of kind of going out, the pink and the blue, and then coming back in and annihilating, they're now kind of finding themselves being pulled apart. So they can't annihilate each other. And therefore they become real particles. At least they continue to persist, though one is ordinary matter and the other is antimatter. Now that itself causes another issue, because it suggests that at the beginning of the universe there's exactly the same amount of matter and antimatter at this point of the universe. But out of all the stuff that exists today, only one particle in a billion is an antimatter particle, apparently. And this is another Goldilocks feature of the universe. There's just the right amount of antimatter towards matter. because if they continue to coexist in the same quantity, they'd have annihilated each other long before now. And where did all the antimatter go? Well, many theories are starting to kind of try and deal with that. It's still an unresolved matter. But let's go back to inflation. Now, in this diagram, this shows the inflation period. Time is running from the left to the right. Or is that how, actually maybe the other way when you're looking at it on the screen. And the space of the universe is inflating anyway from the Big Bang point up to the green circle, showing the inflated expanse of space. Now, inflation takes these non-uniformities of these quantum fluctuations and stretches them, turns them into variations of density, of mass and energy in space. And some of these pairs are starting to kind of associate with each other. So pairs of pink and blue virtual particles have been separated, and they go on to be the sort of dots on the green circle. And these dots represent areas of denser energy within space. And some of them, like the ones in the upper part of the green circle, become two areas which are sort of related in a line. And others, like the middle one, there's three there, and they kind of form a triangle, and others form a little quadrilateral at the bottom. So these groups of 2, 3, or 4 particles as areas of energy go on to become galaxy seeds. This is what is going to give, these seeds of dense energies, areas of energy and matter. These are going to determine the structure of the universe. Now, let's see what these galaxy seeds get up to. This image puts it in a different way, and I apologize, we keep changing perspectives, but we've got the dawn of time up there in the top left-hand corner, and we have that period of expansion, and the brownish disk represents space just after inflation. So we're still within this first tiny bit of a second. And it's dappled to show the variance of the density of mass and energy thanks to the stretching of these pairs and how they are positioned within space, producing kind of areas of energy. Now, it's described that perturbations spread through the plasma like a sound wave, producing this variance in densities of the plasma matter. And these densities also present in the variance of the density of the stuff we talked about earlier, dark matter. So somehow these quantum fluctuations are producing a variance of energy and mass, and that is also being represented in the variance of the density of dark matter. So dark matter is starting to form randomly amorphous shapes within space. Then we go through the next period. When it's after inflation, there's some expansion, and there's a lot of cooling of the plasma stuff. And as the plasma cooled, the various fundamental forces of physics and their associated particles kind of separate out of the plasma. Now, the masses of each of those 15 fundamental particles belonging to the standard model of physics are all considered free parameters. They are what they are. And it's not just the values that each of them has, like their mass, that's important. Just as important is the ratio that the values of their masses may have to one another. For instance, at this time of 1/1,000,000th of a second, the plasma has cooled enough for protons and neutrons to form. Now, protons and neutrons are each made up of quarks, slightly different. Protons have 2 up quarks and 1 down. Neutrons have 1 up and 2 down. And the respective mass of each of them is almost the same. You're probably taught school probably the same mass, but almost the same, but not quite. The ratio between their masses is 1.0014, and maybe a few more decimal places. Now, without this particular critical mass ratio between them, protons couldn't stay as protons. If the weight of a proton was any more, it would collapse into being a neutron. There'd be no atoms in the universe at all. So it's tough enough explaining the precise critical values of individual objects, but we've also got to explain why the ratio between two values, which are meant to be arbitrary, is also so precise. Now, Stephen Hawking commented on this issue. He said, the laws of science as we know them at present contain many fundamental numbers, like the size of the electric charge of the electron and the ratio of the masses of the proton and the electron. The remarkable fact is that the values of these numbers seem to have been very finely adjusted to make possible the development of life. Now, this takes us up to this point of 380,000 years, the time of the cosmic microwave background, when all the electrons and baryons combine to form stable atoms. And we talked about the photons released as the cosmic microwave background radiation. Now, at this point, all those previous perturbations stop being propagated. So whatever was the density pattern at this time became fixed, frozen in space-time. And this variance of the densities is said to be observable within the anisotropies, which is the kind of variance, the differences shown in the different colors in the map of the cosmic microwave background. And that's it. That's the information related to the starting conditions. That, yep, we've got information now imprinted in space-time, which we can read from the cosmic microwave background. But this information has got there because it's been produced by random quantum fluctuations. So essentially, it's a very, very low information state. Those quantum fluctuations technically were just doing their own thing. Why would they represent high specifying information? So low information state representing the chaotic high entropy of the cosmic beginnings. Now we're at the starting point period, determining the actual form that the universe will adopt. And the first bit of this period is called the Dark Ages because it's the time before the formation of any luminous objects like stars, so it's all dark. So besides the atoms and photons that the universe has produced, there's also cold dark matter, CDM rather, and cold dark matter. Now, the areas of high density of dark matter start to collapse or kind of pull together because of gravity and form clumps of dark matter. So dark matter is being affected by its own kind of gravity. So where there are then these intense regions, or sometimes they're called halos of dark matter, then ordinary matter, the real atoms that we would consider, are attracted to and kind of fall into shape around them. And this, and you can see in the picture, we've kind of got the clumping of dark matter during this period. And over time, this process gives rise to the cosmic dawn. And gravity acts on the gas gathering around the clumps of dark matter. And when the ordinary matter is squeezed so tightly by gravity, the reactions of nuclear fusion occur and a star is born. And gravity then keeps on acting and stars gather gases and cosmic debris around them, which form solar systems. And these systems gather into galaxies, and galaxies then form their own clusters of galaxies. And there's consolidation of all of this, and this makes up what is called the large-scale structure of our universe. So during this period from the Dark Ages to the present day, the principle at work, and the main one, is the effect of gravity, pulling together dark matter and ordinary matter to form all the features of the cosmos. But gravity on its own is a low information process. Say we have a batch of matter objects arranged randomly. Now they're said to be in a high entropy state, as we've talked about. One of them in our little group is larger than the rest, so it can exert a gravitational effect on the others. and the group will gradually tend to be gathered because of that gravity effect like this. And because the objects are now located more specifically near the larger central object, you can say the entropy of the group has reduced, but not that significantly. There are still quite a lot of configurations that would retain this similar level of disorder or order. So whereas the following arrangement of the objects entails a much more structured configuration that can be fulfilled by a much more limited set of placements of the cubes. So the third arrangement is a much lower entropy state. Now, we would expect gravity to be able to produce the middle arrangement. That's what gravity can do, pull things together. But we'd be much more surprised if it produced the equivalent of a partially stacked arrangement, where there was some specific setup and configuration of the elements. And hence we say that a process that simply draws other objects to it without adding any further information about location and configuration is a low information process. And this is true whether the objects are static, as in our diagram here, or moving in orbits around a cosmic object, whether it's a star or a black hole. And just as the ability of our little cubes to get close to the central cube depends on their individual properties, so the configurations and movements of planets, stars, and galaxies depend on their individual properties and abilities to interact with other objects according to the laws of physics. But it essentially remains a low information process. Now, I've given a very simple summary of what is a complex analysis by physics and mathematics of the theory and the standard model of cosmology. However, the point is that at the heart of the processes are arbitrary laws and occurrences arising from very high entropy states. And these should have very low information content. And although gravity is assisted in producing cosmic structure by the underlying template of dark matter clumping, that template of dark matter itself is the product of low information processes, the random occurrences of the vacuum fluctuations producing the pair of particles. That's random. That's low information. The effect of inflation on those pairs so they can't deny, that's a low information process. The stretching of non-uniform quantum information into something bigger in space, that's a random process. So dark matter and its clumping, which is said to be the template, is a product of processes which are essentially random, arbitrary, and low information. Hence, according to the standard model of cosmology, the universe begins with very, very low, non-specific information. And subsequent outcomes are also the result of low information processes. Whatever happens after that, the only additional thing that seems to be at work after this period of setting up the kind of dark matter template is the effect of gravity, a low information process. And on all of this hangs the structure of the universe. So to summarize, considering the issues of entropy and structure that we've discussed, and how these are hard to resolve by reliance on the low information processes such as gravity and dark matter clumping that are inherent in the standard model for the formation of cosmic structure, unless there is sufficient defining information established in the early universe and that actually permeates that template. And that is the next question. Is there sufficient information from the early universe? But no. Given how it's described, there is an assumed high entropy state at the start of space-time as a singularity, and in the chaotic state just after and during inflation. So the beginnings and early universe are a state of ultra high entropy and extremely low information. Yet, we find there are numerous instances of constants and parameters that seem to have been precisely set to enable the universe to unfold as it did. Now, this set of thoughts has led many cosmologists themselves to wonder, if we are able to explain the information content of the universe as it is now, do we have to ask the unthinkable question? Is there something before the start of the universe, before t equals 0? And I say unthinkable because time and existence is itself supposed to start at the 0 point. And for some, asking what happened before time, what happened before the Big Bang, is like asking what's north of the North Pole. It's a paradoxical, senseless question. But for others, the analysis and summary that we have given, which is drawn from their kind of musings and ideas, begs the question, might there be some pre-existing factor that provides our newly hatched universe with a set of information that ensures its successful development? So is there some pre-existing factor that is responsible for the information that ensures the successful development of the universe as we see it happening? Now, lots of different answers have been suggested. Some are naturalistic. They are to do with the extrapolations of principles of physics and cosmology. And some are stochastic. They consider probabilities and possibilities. Some are theological. God did it. But how do we check and investigate that? And there are also versions of the anthropic principle, both strong versions of that, and we'll talk about that a bit next week, that the universe is somehow or other tuned to produce life. And we're going to do our best to sift through those issues of what might exist prior to t equals 0. And we're going to look at them, as we have done, from our philosophical viewpoint. How can we analyze such ideas and the logic? And we want to see what insights will explain the evidence, and evidence not just for cosmology, but for all the other aspects of our existence. And in these next few talks, to finalize the part 4 of the Atma Paradigm, I think what we're really looking for is a standard model. Not just a standard model for cosmology, but a standard model that covers all of the 4 big questions together: consciousness, matter, life, and the universe. Big challenge, but we've probably got some ideas that might help. So join me next week as our journey continues, this time beyond the start of the universe, and where we enter the realm of pre-temporal reality. And it'll be the same time next week temporarily, at 6 p.m. UK time, Thursday the 19th of November. And as always, please send any kind of comments or ideas, questions to info@s-pi.org.